So now that we've started solving first order differential equations using the method of separable, what if separable doesn't work? Not every differential equation first order differential equation is in fact separable. So what we want to do is look at other methods for solving first order differential equations. We're going to first look at ones that happen to be linear equations. A linear equation of first order is whenever you have a1 of x times dy dx plus a0 of x times y equals g of x. So as a reminder, the reason it's linear is because the a1, what's being multiplied by the dy dx does not have a y in it. What's being multiplied by the y does not have a y in it. They're just factors of x. They can be anything. They can be nonlinear functions themselves, but what makes it linear is the dy dx and the y have no y's times them. So, and the g of x is just a g of x. This is in one form. We actually want to put in what we call standard form, which just means we're dividing through by the a1 of x. When we do that, we get dy dx plus, we'll call it p of x times y equals f of x. We'll call that f of x instead, where p of x is a0 of x divided by a1 of x, and f of x is g of x divided by a1 of x. We just divided through by a1 of x to get a 1 in front of the dy dx. One thing to remember is that when you divided by that, the a1 of x had to be not 0. So we do have to assume that your I is going to be where p of x and f of x are continuous. a1 of x equal to 0 will actually give you a singular solution. So we now have this. We have a1 of x y prime plus a0 of x times y equals g of x. If we were to let g of x equal 0, then we would have a1 of x times y prime plus a0 of x times y equals 0. This is called a homogeneous equation. This idea of homogeneous equations come up lots of different places in differential equations. This is the first time we've seen them. So please pay attention to this concept and understand this definition. So we end up with y prime plus p of x times y equals 0 when we divide through by the a1. If it's not equal to 0, it's called non-homogeneous. And again, this idea of homogeneous and non-homogeneous does play a lot in our solving of differential equations. The solution to dy dx plus p of x of y equals f of x has the form of some function y equals y sub c plus y sub p, where y sub c is the solution to the associated homogeneous equation, and y sub p is the particular solution. It's the solution to the non-homogeneous equation. And so we're going to look at how those all fit together. So let's start off with the associated homogeneous equation. dy dx equals p of x times y equals 0. Well, if I solve for dy dx, I get dy dx equals negative p of xy. Well, that's separable. So we can solve that. We already know how to solve that. So y sub c, if I were to separate this, multiply through by the dx, divide through by the y, I'd end up with my complementary solution, which is what this actually called. My y sub c is c e to the negative integral of p of x dx. Y sub c is equal to c times y1. So if we pull that c off and just look at that y1 by itself, then you have y sub 1 is equal to that e to the negative integral of p of x dx. So that's kind of where we're looking at here, is we're thinking of just what that y1 is, because the c is just a constant. So now to find the y sub p, we're actually looking at the derivative of y1 dx plus p of x times y1 equals 0. We know that because we just found y1 by being the solution to the homogeneous equation. So to find y sub p, we're going to use a method called variation of parameters. This method actually comes up later when we solve more complicated differential equations. And we're going to use it here too. So we're going to find some function mu such that y sub p equals mu of x times y1 of x. In other words, we're going to kind of in a way guess what that mu sub x is. And then your y sub p is that function we kind of guessed at, or discovered, I should say. I won't call it guessing because it's not really like you're just going to pick one and try it. We're going to actually discover what that mu of x is And then we're going to multiply that by that y1, that homogeneous solution, that y sub c part of the solution. And that will give me my particular solution. And that's your solution to dy dx equals p of x times y equals f of x. So if it's a solution, I can plug it in. If it's a solution, I know it will make this equation true. So I can actually plug this in to this differential equation, which means I got to take the derivative of this. So the derivative of y sub p, of course, is just using the product rule. It's the derivative of the first times the second plus the first times the derivative of the second. So all I did was the product rule on what my y sub p is equal to, plug that in for y of x dx, and then p of x times my y, mu sub x, y1 of x equals f of x. I notice that these two terms have a mu of x in it. If I pull that mu out, I end up with dy1 dx plus p of x times y1. And we've got this other term here, the d mu dx times y1. So we have all that. But I want to point out something to you. dy1 dx plus p of x times y1, that was my homogeneous equation. That is, in fact, the equation that we did up here. That was my homogeneous equation up here, and we said it was equal to 0. So this is actually equal to 0. So this just goes away. So that term is now gone. So dy dx, I'm sorry, d mu dx times y1 equals f of x is what we have left. But that's separable. So if that's separable, solve for the d mu equals f of x over y1 dx. So mu is equal to the integral of f of x y1 dx. Well, that doesn't look very nice. That looks kind of complicated because it's got a y1 and an x. But remember, y1 is e to the minus the integral of p of x dx. So we can plug that in. So we get mu is actually equal to the integral of f of x over e to the negative the integral of p of x dx, all times dx. Now everything has an x in it. We can find this integral. So mu is equal to this integral of f of x. Make it a little bit simpler, bring that up to the top, e to the integral of p of x dx. So if that's what mu is, that means my y sub p is that mu times y1. So it's this integral of f of x, integral the e to the integral of p of x dx, all dx, times y1, which was e to the negative p of x dx. I know this looks really complicated, and actually we don't go through this method. We don't actually use this exact method every single time. I'm not going to ask you to go through and use this formula. I'm just trying to show you kind of the method we use, and then we'll go into that. A little bit farther, we can say y now is equal to c1 times y1 plus y sub p. y1 was e to the negative p of x dx. So we have c e to the negative p of x dx plus e to the negative integral of p of x dx times the integral of f of x e to the integral of p of x dx. There's an awful lot of e's to here. In fact, there's an awful lot of e's here. And if I were to multiply through by e to the integral of p of x dx, then what I would end up with is I'd end up with e to the integral of p of x dx times y on the one side, c as the first term on the right-hand side, because those e's would cancel, and these e's would cancel, so you're left with plus the integral of f of x e to the p of x dx. That e showing up a lot of places is actually e to the integral of p of x dx is actually known as what we call the integrating factor. So that's actually what we do is we try to figure out what that integrating factor is, and then we use that to solve the differential equations. So we don't actually, all the thing we just went through here was just to kind of talk about what is that integrating factor. We don't actually go through what we just did every single time, but I will show you what we do go through. This is known as a method of integrating factor. We're going to first put that differential equation in standard form. So make sure you get the dy dx with a 1 in front of it, plus p of x times y equals f of x. Then you're going to find that integrating factor. Well, it's just e to the integral of p of x dx. So once you figure out what that p of x is, which whatever in front of the y is your p of x, then you're going to multiply your standard form by that integrating factor and then solve what's left. To show how this works, let's go ahead and do an example. So let's solve 3 times dy dx plus 12y equals 4. This is my differential equation I want to solve. So first thing I'm going to do is get it in standard form, divide through by the 3. So I'm going to do that. So dy dx plus 4y equals 4/3. And so now I want to find that integrating factor. And that integrating factor is e to the integral of p of x dx. So if I can figure out what my p of x is, I can just plug it in and solve that. P of x will just be functions of x, so everything will work out. Well, the p of x is whatever is in front of your y. So in this case, my p of x is just the number 4. So I just need to find out what is equal, what e to the integral of 4 dx is equal to. Well, that's just e to the 4x, because the integral of 4 is just 4x. So we now have our integrating factor. We know what that is. So now we're going to multiply our differential equation by this integrating factor. E to the 4x dy dx plus 4 e to the 4x times y equals 4/3 e to the 4x. Okay. And you're like, well, that doesn't look any easier. That looks more complicated. I have no idea what this is and why do we do this? But there actually is a reason we did this. And the reason we did this is looking at this e to the 4x dy dx plus 4 e to the 4x times y. If you might notice something about this. And what you might notice about that is that this happens to be the derivative of e to the 4x times y. So, and if you don't believe me, try it. Find the derivative of this. This is a product, so use the product rule. So it's the first times the derivative of the second, but since I don't know the derivative of y, it's just dy dx, plus the derivative of e to the 4x is e to the 4x times 4 times the second y. So you see it will work out every single time. So those two terms always will be the derivative of your integrating factor times y. Whatever your integrating factor is, find that integrating factor first, then multiply by y, and that will be, the derivative of that will be these two terms here. So it looked a little bit more complicated, but it actually simplifies a bit easier. And now all I got to do is realize that I could just take the integral of both sides. And the integral of a derivative, remember, is just the thing inside. So the integral of this derivative is just e to the 4x times y. And then you just define the integral of 4/3 e to the 4x. You can use any way you want. This is actually a substitution problem. You can do a table of integrals if you want. You can use technology to do it. It doesn't really matter. In this case, you just want to find that integral. So that integral happens to be 4/3 times 1/4 e to the 4x plus c. Don't forget your plus c. So now all I gotta do is get y by itself because we're done doing integrals. There's no more integrals. There's no more derivatives. We've got everything. We just need y by itself. Divide through by e to the 4x. That will give me 1/3. Dividing through by e to the 4x means those e to the 4x's cancel. Plus c divided by e to the 4x, which is c e to the negative 4x. And there's the solution to that linear differential equation. And if you want to find out if it's true, you can always take the derivative of that and plug it in and see if it works. We also found the complementary solution. The y sub c is right here. And the particular solution. They're right there. So we don't need to worry about finding those. This method finds both at the same time. Let's try another example. Let's try x times y prime plus 1 plus x times y equals e to the negative x sine of 2x. So the very first thing is get the y prime to have a 1 in front of it. So I get y prime plus 1 plus x over x times y equals e to the negative x over x sine of 2x. All right, so now that we've done that, now we will go ahead and find our integrating factor. And that is always e to the integral of p of x dx. But p of x is just whatever's in front of your y. So in this case, it's 1 plus x over x. So we're going to have e to the integral of 1 plus x over x dx. So you got to find out what this integral is. This is actually not a hard integral. That if you separate this as the integral of 1 over x plus 1, and the integral of 1 over x, of course, is natural log x, and the integral of 1 is plus x. So we get e to the natural log of x plus x. That's e to the natural log of x times e to the x. E to the natural log of x is x, and e to the x is just e to the x. So there is your integrating factor. We are then going to, again, multiply x times e to the x, that integrating factor, times both sides of the equation. So we get x e to the x times y prime plus x e to the x times 1 plus x over xy is equal to x e to the x times e to the minus x over x sine of 2x. So now just simplify this a bit. You've got x e to the x times y prime plus e to the x times 1 plus x times y. On the right-hand side of the equation, the x's cancel, the e to the x's cancel, and just have a sine of 2x. Again, these two terms on the left-hand side of the equation are the product rule of the derivative of x e to the x times y. Your integrating factor times y. Whatever your integrating factor times y is, that's what the derivative of that would be, these two terms. Again, if you don't believe me, try it. You're going to have the first x e to the x times the derivative of the second, which is just y prime, plus the derivative of the first. We have to use a product rule here. That'll be 1 times e to the x plus x times e to the x, which gives you e to the x times 1 plus x equals times y. So it worked out. Again, it should always work out. It's a good check to make sure it did. Now just take the integral of both sides. The integral of a derivative is just a thing inside, fundamental theorem of calculus. The integral of sine of 2x is negative 1/2 cosine of 2x plus c. And then just get y by itself. So y is going to be negative 1/2. We'll put the x e to the x in the bottom times cosine of 2x plus c times, and I can do 1 over x e to the x. Some people like to bring the e to the x to the top and make it e to the negative x. That's up to you. But there's your solution to this linear equation. And that's all there is. Now, one thing I will point out is I did make an assumption back up here at the very, very top. I didn't mention it at the time, but the assumption was made. When I divided through by x, I had to make the assumption that x could not be 0. So in fact, if you look at this equation, x equals 0 will never get me a solution to this. So this will never actually produce a solution. So that means it's actually a singular solution. So x equals 0 produces, I should say, not itself, but it produces a singular solution. And that actually causes some major problems. So we want to make sure we ignore that. Okay, let's look in, if a term in the solution contains e to the negative x, it is called a transient term. So coming back here to the one we just finished, if I were to write this with e to the negative x, get the e to the bottom, this is a transient term, and so is this xc term. So both those are transient terms. What that means is that x goes to infinity, e to the negative x goes to 0. You're going to see these a lot, especially when we're dealing with anything that has any physical property where you're going to have the quantity you're dealing with going to zero, and that will make it go to zero. And so it's what we call the transitive term. We also can talk about non-elementary functions. These are functions that do not have antiderivatives. They're also called non-analytic functions. There are special ones. One of the special ones is called the ERF of x. It's 2 over the square root of pi. Then you go from 0 to x of e to the negative t squared dt. This is known as the error function. The ERF c is also one. It's got a slightly different. It's e to the negative t squared. It's called the complementary error function. Another one that we see is psi of x. That's the integral from 0 to x of sine of t over t dt. This one shows an awful lot in electrical engineering. Let's do one more example. This one will be an initial value problem. So when we're done, we'll have to find that initial value. So again, I want to solve this and find out what we're going to have. Now, one thing to point out here is that it's dx dy is what we have. So this means that x is my dependent variable and y is my independent variable. So pay attention to that at the start. It's not that y is my independent variable and my dependent variable this time. This one we switch because it's dx dy. So do pay attention to that. So I'm going to divide through by y. So I divided through by y, and the reason I also pointed out is it is linear because x is now my dependent variable and we are linear in x. So we are fine. Let's go ahead and do find your integrating factor. The integrating factor will be e to the integral. Instead of p of x this time, it's going to be p of y dy, because y is now my independent variable. My p of y is negative 1 over y. So we're going to have e to the integral of negative 1 over y dy. Well, the integral of e to the negative, the integral of negative 1 over y is negative the natural log of y. So we have e to the negative natural log of y. Take the negative sign up. You've got e to the natural log of y to the negative 1, which of course e to the natural log of anything is just the anything. So it's just y to the negative 1 or 1 over y. So my integrating factor is 1 over y in this case. I'm now going to multiply every single term by 1 over y to get 1 over y dx dy minus x over y squared is equal to 2. Because I'm again multiplying through by 1 over y. All right. This time, because x is my dependent variable, this is actually the derivative with respect to y, is going to be my integrating factor, which is 1 over y, times x, because x is my dependent variable. Again, if you don't believe me, try the derivative of this. The derivative using the product rule is going to be 1 over y dx dy minus the derivative of 1 over y is negative 1 over y squared. So that's where that comes from. Equals 2. Now take the integral of both sides. We're taking the integral with respect to y this time instead of x, because x is my dependent variable and y is my independent variable in this case. Again, the derivative of the integral of a derivative is just the thing inside. So 1 over y x is equal to 2y plus c. Get x by itself. So we get x is equal to 2y squared plus c times y. Wonderful. But we did have an initial condition. The initial condition was y of 1 is 5. Well, this initial condition is written not the way this is. This initial condition was actually written as x is 1 and y is 5. So it actually is written a little differently here. So we need to remember x is 5 and sorry, x is 1 and y is 5. So x is 1. So everywhere you see an x, you're going to put a 1. And everywhere you see a y, you're going to put a 5. So that lets you solve for c. So it turns out c is equal to negative 49/5. So x is equal to 2y squared minus 49/5 times y. In this case, if I want to find out if I have any singular solution issues, I divided through by y. So my I couldn't let y equal 0. So my I could either be negative infinity to 0 or 0 to infinity. Being a physicist, I like positive independent variables. So I'm going to have my y be 0 to infinity. And that's how we solve different equations that are linear.